Okay, let's look at this physics question. Let's look at this particular question. Which of the following equations correctly relate U and V? Okay. Now, what we have to do is to look at the momentum before the collision and the momentum after the collision. Okay, before we discuss about this, let's look at the three situations. Okay, if the collision is elastic, kinetic energy is conserved, momentum is also conserved. If inelastic, then some kinetic energy is lost, but momentum is still conserved. Now, if perfectly elastic means the two will, after the collision, the two objects will stick together and move at the same speed. Okay. Now, in this case, momentum is still conserved, but the energy loss is the greatest in this case. Okay. Now, to look, the equation that you have to cater for these three special cases is this. Okay. Okay, you take a look. But for the third one, the M1 and the M2, since they are stick together and travel at the same speed, then you put the M1 plus M2 together. Okay, the difference between inelastic and elastic is you cannot use the energy equation to solve. Similarly, for this case, perfectly inelastic, you cannot use the kinetic energy equation, the energy equation to solve the unknown. Okay, the only thing you can use that's common for the three is the momentum is conserved. Okay, so the only thing you can do is this. Like the first question where it doesn't mention anything, then it can be any of these cases, but it's okay because in any of these three cases, the momentum is conserved. So we're going to use this. Look at this. Okay, first, now, after the collision, the object move this direction. Okay, no more in the horizontal direction. Then this object itself and also move in non-horizontal direction. So in other words, they have component horizontally. If you convert this into the vertical component and the horizontal component. Similarly here, also you can break down into vertical component and horizontal component. Okay, now, so if the momentum is conserved, means the horizontal momentum must be the same. Now, what I mean is, you see, you start off with horizontal speed, so whatever momentum created here in the horizontal position must be equal to whatever component that you have produced here. Okay, now, then you have the vertical component. The vertical component, they must be zero because at the very beginning there is no vertical momentum. Okay, so whatever momentum that is created, the sum of them must equal to zero. Okay, now let's start off with let's look at this diagram. Okay, you can see that this component, the momentum, actually can split into this direction and also this direction. Okay. Similarly, for this object, the momentum can be split into this direction and this direction. Okay. But then at the very beginning, there is no vertical component, no vertical momentum. So it means to say if the momentum is conserved after the collision, then this momentum must be same as this momentum, so that they cancel off each other, so resulting in no vertical momentum. Okay, now let's find out what is the momentum in the vertical direction. So your momentum in the vertical direction would be this one. Okay, so if you use trigonometry, you know that this momentum is actually vertically up. Okay, vertically up, this momentum is actually 2m sine 30. The weight times the speed. The speed, if you convert the speed, which is u, okay, if you convert into the vertical component, it will be u sine 30. So this is the mass 2m, then the speed is u sine 30. Okay, now vertically down, this is produced by this object here. So vertically down component is this one. Okay, now so the mass is m, and then the velocity is since this v, so it's sine v sine 60. We give you the vertical component. Okay, so v sine 60. Okay, now remember at the beginning there's no vertical component. After the collision there's two components created, but according to the rules, the component in the vertical direction is 0. That means they are equal to each other. To cancel off, they end up a zero zero component in the vertical direction. So what we can do is we put them together. They has to be equal to m u sine 30 equal to mv sine 60. Cancel off the m. Okay. Then you got 2 u sine 30 equal to v sine 60, which is C. Okay, now then let's go to the next. Next question, if it's elastic, then the kinetic energy is conserved. Okay, as we know, energy is not a vector, it's just a scalar. So we will calculate the kinetic energy of this object at the very beginning, and then we will calculate the kinetic energy of this object 2m after the collision, and we also calculate the kinetic energy of this m after the collision. That means the kinetic energy before and after must be the same. Okay, now so let's look at the energy before the collision. Before collision is equal to 2m half times m, which is we are talking about this mass here, 2m, the velocity is u square plus half this m, but the speed is 0. Okay, so what you have is you cancel off. You got m u, the big U square. Okay, now the kinetic energy after collision is equal to half time. Let's look at this. Okay, this object, the mass is 2m, and then the speed is u, small u square. That is for, this one is for the 2m object. Now let's look at the m object is equal to half time m time v square. Okay, now let's simplify this. If the kinetic energy is conserved, that means this, which is the kinetic energy before collision, and big U square must equal to this one cancel. You got m u square plus half m v square. Cancel out the common factor, which is m on both sides. So what remains is u square equal to u, small u square plus half v square, which is this. Okay, so that's it.